Hello guys, this is Math for Fun, and today we're going to be showing why Euler's formula is true. So Euler's formula makes the following statement. It makes a statement that e to the ix equals cosine of x plus I sine of x. All right, and we're going to prove this using Taylor expansion. So I want to preface this by saying if you don't know what Taylor expansion is and you're trying to watch this video to understand the conceptual reasoning as to why this formula works, this is not the video for you. There are a lot of other cool videos about why e to the ix equals cosine of x plus I sine of x, or if you're particularly curious about why e to the I pi equals -1, I encourage going to, I'll write it up here, 3 Blue 1 Brown's channel. And they have a very good explanation as to why e to the I pi equals -1 using just basic derivatives. So obviously Taylor expansion is a more complicated topic in calculus, but if you only know derivatives, you can prove this really cool formula using the derivative of e to the x, and that is itself. All right, so now that we got that out of the way, we're going to prove this formula using Taylor expansion. All right. And how are we going to do that? We are going to do the following. We're going to write the Taylor expansion for e to the x, cosine of x, and sine of x. That's what I'm going to do first. So I'm going to delete this for now. Okay, so the Taylor expansion for e to the x is as follows. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and this goes on forever. All right, and I'm hoping that makes sense to the people watching the video. And I just got to make sure that that is indeed correct. Yep. Okay, sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus 7 to the x over 7 factorial, and this goes on forever. And the expansion of cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and this goes on forever. All right, so I want you guys to, if you are trying to follow this along, I would recommend maybe writing this down, taking a picture of this, because I'm going to go into another slide in a moment here, and we're going to use these to prove the formula above. All right, so on the previous slide, we showed the Taylor expansion for e to the x, but in our Euler's equation, we have e to the ix, all right? So we want to create a Taylor expansion for e to the ix, which is actually really simple. We just take all of the x terms in our original Taylor expansion, and we turn it into ix. All right, so we get 1 plus ix, all right, plus ix squared over 2 factorial, and this goes on forever. All right, and an important thing to note here is that when you take I and you raise it to a certain power, we know that I to the 1 is I squared is -1, I cubed is -I, and I to the 4th is 1. And then this pattern repeats, all right? And the idea that this pattern repeats is going to be important here, because if you notice, in our Taylor polynomial, we have these I terms being squared by numbers that are increasing by 1 each time. So here, I'm going to do this really cool tool here. Here, I is going to be squared by, I is going to be exponentiated by 2. I believe that's correct terminology. In the next term, 3 is going to exponentiate I, and that's going to be 4. So this important nature of how you raise I to exponents and you get this kind of repetition is going to be important in creating the full expansion for this polynomial, because what you're going to end up getting is this ends up equaling 1 plus, I'm going to write it all the way on the bottom so I have more space, equals 1 plus ix minus x squared over 2 factorial minus ix cubed over 3 factorial, and then plus x to the 4th over 4 factorial plus ix fifth to the 5th over 5 factorial, and this pattern repeats forever. All right, so that's e to the ix. All right. So next, I'm going to rewrite our cosine expansion at the top, which from our last thing was cosine of x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and this goes on. This pattern repeats. And now we want to make a Taylor polynomial for I sine of x, all right? And we have a Taylor polynomial for sine of x, right? So if we know that sine of x equals this, then I times sine of x is all of this multiplied by I, or essentially every single term in this polynomial is being multiplied by I. So we got to add an I term into it. So this actually ends up being really simple. It's going to be equals ix minus ix cubed over 3 factorial plus ix to the 5th over 5 factorial. And this goes on forever. All right. And the idea that this pattern and these patterns repeat, so this pattern repeats indefinitely, all right, going this way. This pattern repeats indefinitely going this way, and this pattern repeats indefinitely going this way is going to be very important because we can now do some grouping. If you notice, every other term in our e to the ix expansion lines up with cosine, all right? So if you notice here, we have 1, and here we have 1. Here we have negative x squared over 2 factorial, and here we have negative x squared over 2 factorial, and every other term is going to be the same as cosine of x. So what we can do is we can cross out every other term here and just replace it by adding a plus cosine of x. All right, so e to the ix equals all of these terms plus cosine of x. So now we look at these terms. Well, these terms are the same as I sine of x, right? We have ix here, negative ix cubed over 3 factorial here, negative ix cubed over 3 factorial here. I had a monster lisp there, I apologize. And ix to the 5th here and ix to the 5th here. So we can replace all of these terms because this pattern repeats indefinitely. We know that it will continue going this way, and all of these terms equal I sine of x. All right. So we can then say that e to the ix finally equals cosine of x plus I sine of x. And there is Euler's formula. And there's two kind of really important things to take away from this formula. The cool thing about this formula is you can use it to prove the most amazing, inarguably amazing, I just stuttered there, or had a brain fart, the inarguably most beautiful equation in math, which is the e to the I pi. Actually, I'm going to write it better. E to the I pi plus 1 equals 0. And it connects all of the mathematical constants, all the important mathematical constants, well, not the big mathematical constants that you hear of, e, I, pi, 1, and 0, all very important numbers, into one elegant equation. And it's really goddamn cool that this is true, and we just prove why it's true using this formula, which is really, really cool, because using this formula, if you plug in pi for x, you get -1 for cosine and 0 for sine, so the imaginary term goes away, and you're left with -1. So takeaway number one, big takeaway number one, is that you can use Euler's formula to prove this very beautiful equation. But all right, so takeaway number 2 from Euler's formula is that we can use Euler's formula, which I'm going to rewrite, to expand our definition of exponentiation into the complex numbers. What do I mean by that? Well, before this, we really only knew how to raise numbers to real numbers, right? If I told you before this to tell me what is 2 to the I, you'd probably be like, I have no idea. But before, if I told you, like, what's 2 to the 1/2? Or 2 squared, you'd be like, oh, that's √2, or oh, that is 4, right? So our definition of exponentiation makes sense when we talk about real numbers, all right? But it breaks down when we start to talk about imaginary numbers, or even harder, complex numbers. Like, what the hell would you say is 2 to the 2 plus I, right? We don't know. But using Euler's formula, we can actually write a very beautiful way to raise any number to a complex number, all right? And before we talk about complex numbers, let's actually talk about raising any number, a, which is a real number, to an imaginary number, I times x, where x is some constant. All right. For starters, we know that things get a lot easier when we start dealing with like e to the ix or e to the I times something. So the first question that arises is, can we rewrite this in terms of e to the ix? And it turns out we can using log properties, all right? So a to the ix equals e to the ln of a to the ix. And that stems from log properties, which I hope you understand. If you raise e to the natural log of something, whatever is in the argument of that natural log will be what this expression is equal to. All right, so I'm going to replace a to the ix with e to the ln a to the ix. And using log properties, what we can do is we can actually bring this I and x to the front. So this ends up equaling e to the ix times ln a. All right, so if we go to actually I'm not going to go to another slide here. Or I will. So we now can say that a to the ix is equal to e to the ix times ln a. All right, so using Euler's formula, we can then say this all of these equals cosine. All right, and in this case, our x value is x ln a, x times ln a, plus I sine x ln a. All right, so a to the ix, a raised to any imaginary number, is equal to this. All right, where you take the x value, right, and you put it up here, and the a value is going to be the natural log here, and we just prove why that's true. So if we want to raise a to a complex number, which we're going to say, let's say is a to the b plus ci. It's unfortunate we can't say a plus bi here, but we're just going to say a to the b plus ci. All right, using exponential properties, we know that a to the b plus ci is equal to a to the b times a to the ci. All right, and using the definition of exponentiation that's already familiar to us, we know how to evaluate a to the b because b is a real number. And using this, which we just proved, we know how to evaluate a to a purely imaginary number. All right, so we take the product of these two numbers and we get our answer for what a to the b plus ci is. And I'm going to write it. So a to the b plus ci equals a to the b times a to the ci, which we proved is cosine of x ln a plus I sine x ln a. All right, so here is another formula you get from Euler's formula, and it expands our definition of exponentiation into the complex numbers. So that's another big takeaway from Euler's formula. We now have a new definition for complex numbers, not complex numbers, for exponentiation in the complex plane. I keep saying it, I'm probably repeating myself and beating a dead horse at this point, but it's really, really important because now raising a number to a complex number makes sense. All right, so that's another big thing that came out of Euler's formula. And hopefully you take that away from this video.